What is the theoretically fastest possible speed of a sorting algorithm? In this video, we'll aim to answer this question for comparison sorting algorithms. These are algorithms that sort arrays by comparing elements. They receive no extra information about the elements being compared, such as their absolute size. Many of the sorting algorithms in widespread deployment are comparison sorts. Popular examples include insertion sort, heap sort, and quicksort. Our question has an interesting history. In his legendary book of mathematical snapshots, Polish mathematician Hugo Steinhaus considered the puzzle of ranking players in tennis tournaments. In particular, he asked how few matches could be used to rank all the players. Entertainingly, he also notes that the custom of giving the second prize to the losing finalist in a competition is, to a mathematician, obviously unjust, since this player has not been compared with other players who lost to the finalist. Clearly, Steinhaus is a man who would be appalled by the travesty of fairness that is college bumps racing, where the winner can technically be the slowest boat in the race. Steinhaus then went on to propose a tentative lower bound on the number of matches required to rank all players. In 1959, Lester Ford and Selma Johnson introduced an algorithm known as merge insertion sort, together with a simple decision tree analysis that can be used to prove lower bounds. Many other results have been proven since then, but the key runtime complexity results that we'll be interested in are the following. First, our lower bound for the runtime of the worst case input to an algorithm is big omega of n log n. No comparison sort can possibly do better than this on its worst input. Second, our lower bound for the average input to a comparison sorting algorithm is also big omega of n log n. Note that the former immediately implies that comparison sorts like heap sort are asymptotically optimal. However, it's also important to keep in mind that non-comparison sorts like radix sort can do better than this lower bound by exploiting extra information about the structure of the problem. To make things concrete, we'll define a comparison sort as an algorithm that ingests an array of n elements, a0 up to an-1. It only gains information by comparing pairs with questions of the form, is ai less than aj? The sorting algorithm outputs a permutation that orders the items into ascending order. For our analysis, we will assume that all elements in the array are distinct, since repeated elements won't affect the lower bounds we are interested in. A useful tool to analyze comparison sorts is the decision tree, sometimes also called a comparison tree or a questionnaire. These are full binary trees, which is to say each node has either 0 or 2 children, where each internal node of the form i:j represents a comparison between ai and aj. Each leaf node represents an array permutation that sorts the input. Let's look at a decision tree when sorting an array of 3 inputs. At the root, we ask whether a0 is less than a1. If yes, we ask if a1 is less than a2. If yes, then we have found the output permutation, which is 0, 1, 2. If no, we ask whether 0 is less than 2. If yes, the output permutation is 0, 2, 1. If no, the output permutation is 2, 0, 1. By answering other binary yes-no questions, we can similarly complete the right-hand side of the tree. The usefulness of this structure comes from the observation that each time we run a comparison sort on an input array, we are following a particular path from the root node to the leaf that represents the permutation that sorts the inputs. Now we have the decision tree concept, we can take on our first lower bound. We start by noting that there are n factorial possible permutations, without repetitions, that represent the various ways to sort an input. Given all the possible ways of ordering the input, a correct comparison sorting algorithm must be able to produce all of these n factorial permutations. So, a comparison sort decision tree corresponds to a full binary tree with at least n factorial leaves. The worst case input is the one that requires the most comparisons to sort. This is the length of the longest simple path from root to leaf in this tree. To find this longest path, we can equivalently ask, what is the maximum height of a decision tree? Since a binary tree of height h has at most 2 to the h leaves, we can infer that n factorial is less than or equal to 2 to the h for a decision tree that corresponds to a valid comparison sort. At this point, it's useful to note Stirling's approximation, which gives us an expression for n factorial, which we can use as an upper bound on a slightly simpler expression. Pulling this all together, we have that the height of the tree h is greater than or equal to log of n factorial, which is greater than or equal to log of n over e to the power of n, which we can break apart into log terms to give an expression that is big omega of n log n. This gives us the lower bound on comparisons for worst case inputs. That is to say, no comparison sorting algorithm can be faster than this on its worst case input. We can use similar ideas to give a lower bound on the average case. Here we instead ask, what is the smallest possible average height of a decision tree? The average height is smallest when the tree is completely balanced, where the term completely balanced means that no leaf heights differ by more than 1. If the tree is completely balanced, then each leaf has a depth of either the ceiling of log of n factorial or the floor of log of n factorial. Using the same logic as for the worst case, we have that the smallest possible average height is big omega of n log n. That is to say, no comparison sort can be faster than n log n on average. In the video description, you can find links to slides and references. I hope you have a wonderful day.